The research paper presents a groundbreaking technique for the analytical evaluation of multifold Mellin-Barnes (MB) integrals, commonly encountered in physics, particularly in the calculation of multi-loop multiscale Feynman integrals. This approach is based on triangulating a set of points associated with a given MB integral, resulting in final analytical results expressed as linear combinations of multiple series. Each triangulation allows the derivation of one of these combinations, with the involved series being of the multivariable, hypergeometric type when applied to Feynman integrals. The authors implement their method in the Mathematica package MBConicHulls.wl, an existing software dedicated to the analytical evaluation of multiple MB integrals. This software uses a computational approach based on intersections of conic hulls developed recently. The triangulation method is significantly faster than the conic hulls approach, making it suitable for calculating higher-fold MB integrals. To demonstrate the efficacy of this technique, the authors compute triangulations for complex objects such as the off-shell massless scalar one-loop 15-point Feynman integral, which has 104 folds in its MB representation. Other applications include providing new results for the off-shell massless conformal hexagon and double-box Feynman integrals, as well as for the hard diagram of the two-loop hexagon Wilson loop. The paper also discusses the potential of this technique to contribute to future research in theoretical physics, particularly in the context of quantum field theory and string theory. The method's ability to efficiently evaluate high-dimensional MB integrals could lead to significant advancements in understanding complex physical processes and the development of new computational tools for physicists and mathematicians. Mellin-Barnes integrals are a specialized class of integrals employed in diverse areas of physics and mathematics. Their applications encompass the resolution of E-singularities in dimensionally regularized Feynman integrals, the derivation of analytic expressions, and numerical integration. Furthermore, they play a crucial role in the theory of multivariable hypergeometric functions. Recent advancements in computational techniques for Mellin-Barnes integrals have focused on the conic hull approach, despite its limitations. This paper introduces a novel geometrical method for the analytic evaluation of multifold Mellin-Barnes integrals, leveraging triangulations of point configurations. This approach is computationally more efficient and exemplified through its application in finding series representations of Feynman integrals and computing the Wilson loop. The proposed method offers a promising avenue for tackling complex integrals in various physical and mathematical contexts. Computation of n-fold Mellin-Barnes integrals is a crucial step in evaluating Feynman integrals for high-energy physics calculations. To efficiently compute these integrals, a novel technique called the triangulation method is introduced. This approach applies multivariate residues to obtain solutions in terms of multivariable series representations. The general form of an n-fold Mellin-Barnes integral involves a complex set of variables and gamma functions. The triangulation method is based on carefully choosing integration contours that separate the left and right-handed poles of the gamma functions. This choice is critical in ensuring the convergence of the series representation. The authors demonstrate the effectiveness of the triangulation method through several examples. These include the computation of a twofold Mellin-Barnes integral and the evaluation of previously computed Feynman integrals, such as the hard diagram of the two-loop six-edged Wilson loop, the conformal hexagon, and the double box. The method is also applied to compute higher-fold Mellin-Barnes integrals, specifically the endpoint integral with n up to 15, showcasing its efficiency and accuracy. In comparison to the conic hulls computational technique, the triangulation method offers several advantages. It provides a more efficient and accurate way to compute n-fold Mellin-Barnes integrals, making it a valuable tool for future research in high-energy physics. The computer implementation of the triangulation method is detailed in an appendix, providing a practical guide for researchers to apply this technique in their own work. The Mellin-Barnes MB representation is rewritten in canonical form, as shown in equation 3, where the gamma function arguments are expressed as c, z, and t, z, in equation 4. This form is conducive to analytic evaluation using the triangulation method. In this method, a set of k points is assigned to the MB integral, which can be extracted from the arguments of the gamma functions in the numerator of the integrand. These points, denoted as P1, Pk, consist of endpoints whose homogeneous coordinates are built from the coefficients of the z integration variables, and Kn additional points corresponding to unit vectors of dimension Kn, as shown in equations 5 and 6. The point configuration can be represented as a Kn xk matrix, denoted as the A matrix of the MB integral, as shown in equation 7. The next step involves finding all possible regular triangulations of the point configuration P equals P1, Pk. These triangulations are built from a set of simplices, each dualed to a conic hull in the MBConicHulls approach. A bijective correspondence exists between the set of possible regular triangulations and the set of relevant intersections of conic hulls, allowing the association of a set of poles to each triangulation. The multivariate residues of these poles are summed to obtain series solutions, as done in prior work, 20. Ultimately, each triangulation is used to construct a series representation of the MB integral, yielding various series solutions. The triangulation method is applied to the computation of Feynman integrals and the derivation of linear transformations of multivariable hypergeometric functions. This method has been implemented in a new version of the MBConicHulls.wl Mathematica package, enabling the analytic calculation of n-fold Mellin-Barnes integrals with n is greater than or equal to 1. The authors illustrate the triangulation approach by computing the simple twofold Mellin-Barnes integral associated with the Appel f1 double hypergeometric function. The Mellin-Barnes representation of f1 involves a double contour integral of a product of gamma functions, as shown in equation 8. From this integral, the usual series representation of f1 can be derived, as demonstrated in equation 9, which converges for z1 less than 1 and z2 less than 1. The authors also discuss the four analytic continuations of the series representation, which were previously derived using the conic hull method. These continuations can be obtained by labeling the 5 gamma functions of the numerator of the Mellin-Barnes integrand and finding the corresponding conic hulls, as shown in equation 10. In the context of multivariable hypergeometric functions, the Appel f1 function is a specific type that can be defined in a three-dimensional space with two variables of integration. This configuration yields 5 points of consideration, denoted as Pf1, which are visualized in figure 1. The first 2 points, P1 and P2, reflect the s and t dependencies of the numerator's gamma functions, while the remaining 3 points, P3 to P5, are automatically added due to the dimensionality of the configuration space. The corresponding triangulations, shown in figure 2, facilitate the identification of subsets of conic hulls associated with the series solutions. To determine these subsets, one must identify the complements, in the set 1, k, plus n, of the simplices that appear in the triangulations. In this case, with 5 numerator gamma functions, we have 1, k, plus n, equals 1, 5, with k equals 5. By examining the triangulations, the subsets of conic hulls can be deduced. For instance, the triangulation T4 equals 2, 4, 5, 1, 2, 4, 1, 2, 3, yields the complements 3, 5, 3, 4, 5, and 4, 5, representing the subsets of conic hulls. This analysis demonstrates the utility of geometric representations and triangulations in understanding the configuration space of the Appel f1 function, providing insight into the structure of its series solutions. This approach may have broader implications for the study of multivariable hypergeometric functions and their applications in various fields of mathematics and physics. The computation of multivariate residues and series representations of f1 is achieved through the utilization of conic hulls and triangulations. 5 regular triangulations of the configuration of points P, f1, are illustrated in figure 2, corresponding to distinct subsets of conic hulls. Specifically, figure 2d depicts the complements 1, 3, 3, 5, 4, 5, equivalent to the fourth subset of conic hulls in equation 10. By applying the method outlined in 20, the authors compute multivariate residues and obtain various series representations of f1. Applications to Feynman integrals are then explored, focusing on the computation of higher-fold Mellin-Barnes (MB) integrals. A comparison of computation times is made between two versions of the package MBConicHulls.wl, employing conic Hulls intersections and triangulation approaches, respectively. The results indicate that the triangulation approach is more efficient for computing MB integrals with a large number of folds. The package is further tested by computing triangulations and series representations of the off-shell massless scalar one-loop endpoint integral for various values of n, ranging from 4 to 15. Notably, the corresponding MB representations can have up to 10 to the power of 4 folds. These results are novel, even for the simplest n equals 4 case. Additional details about these results can be found in the ancillary Mathematica notebook examples, NB. The evaluation of one-loop and two-loop Feynman diagrams using conic Hulls and triangulation methods is discussed in this section. A comparison of computation times for 5 different Feynman integrals is presented, including the off-shell massive conformal triangle, off-shell massless pentagon, off-shell massless hexagon, double-box conformal fishnet integrals, and the hard diagram of the two-loop Wilson six-edged Wilson loop. The triangulation method significantly improves computation times for these integrals, as demonstrated by the results in Table 1. This improvement is particularly notable for integrals with higher dimensional MB representations. The matrix for the double box, which is essential for understanding the MB representation and its application, is also discussed. The results highlight the efficiency of the triangulation method, making it a valuable tool for researchers in quantum field theory and particle physics. The computation of one-loop endpoint massless Feynman integrals is a crucial task in quantum field theory and particle physics. Two prominent methods for accomplishing this task are the conic Hulls and triangulation approaches. A speed comparison, presented in Table 1, reveals that the triangulation method significantly outperforms the conic Hulls approach for integrals with higher numbers of folds. Notably, the triangulation method has been successfully applied to derive series solutions for the hexagon and double box integrals, yielding simpler solutions than those previously obtained. These solutions are provided in an ancillary notebook. Moreover, the authors have explored higher fold MB integrals by considering one-loop scalar massless endpoint Feynman integrals with generic powers of propagators. The general MB representation for arbitrary n is well known and has been utilized to test the efficiency of the triangulation approach. The results demonstrate a substantial improvement in computation time and complexity when employing the triangulation method compared to the conic Hulls method. This comparison highlights the efficiency and effectiveness of the triangulation method for computing one-loop endpoint massless Feynman integrals, particularly those with higher numbers of folds. The triangulation approach not only provides simpler series solutions but also significantly reduces computation time and complexity, rendering it a valuable tool for researchers in the field. The expression for J, N, nu J, Pj, 0, a pivotal component in the evaluation of multifold Mellin-Barnes integrals, is presented. This expression, denoted by equation 13, is a complex function involving gamma functions, infinite series, and poles. For n equals 3, the analytic expression is well known and can be expressed as a combination of 4 Appel F4 double hypergeometric functions. However, for n is greater than or equal to 4, the intricate structure of the poles in the Mellin-Barnes integrand makes it challenging to obtain analytic results. Despite this, the author's package allows for the derivation of these results for large values of n, as demonstrated by the computation of cases up to n equals 15. Table 2 presents the computation times for the one-loop endpoint integral using the triangulation method, showcasing the feasibility of the approach for larger values of n. The table provides the number of folds, number of terms in the series solution, and computation time for each case. The authors have also numerically verified the expressions obtained using their package against direct numerical integration of the corresponding Mellin-Barnes integrals for n equals 4 and n equals 5. The conclusion and discussion section begins, highlighting the novelty of the presented method for the analytic evaluation of multifold Mellin-Barnes integrals, which is based on the triangulation of point configurations. A novel approach to computing Mellin-Barnes integrals is presented, leveraging triangulation to significantly enhance computational efficiency. By associating a set of points with a given Mellin-Barnes integrand, their triangulations directly correspond to series representations of the integral. This method has been implemented in the updated Mathematica package MBConicHulls.wl, introducing the new module Triangulate MB. The approach is illustrated with a simple example, followed by a demonstration of its improved computational speed compared to previous techniques. This enables handling of Mellin-Barnes integrals with a high number of folds in a reasonable calculation time. The new package options facilitate exploration of the space of series solutions, which can be substantial for complicated Mellin-Barnes integrals. The effectiveness of this method is showcased by extracting new and simpler series representations for the hexagon and double-box conformal Feynman integrals, previously obtained in 22. Additional applications to complicated integrals are discussed, including the hard diagram of the two-loop six-edged Wilson loop in general kinematics and one-loop endpoint Feynman integrals, for which new analytic results have been derived through this computational technique. The presented approach has the potential to significantly expand the range of computable Mellin-Barnes integrals, enabling further research in various areas of theoretical physics. The updated MBConicHulls.wl package, including the Triangulate MB module, provides a powerful tool for researchers to explore and compute complex Mellin-Barnes integrals. The Triangulate MB external module is a crucial component in the MBConicHulls package, processing the output from the MB rep function to compute point configurations associated with the MB integral. It utilizes TOPCOM to identify all possible triangulations, printing the set of poles for each series solution. The module's input arguments include MB rep out, representing the output of the MB rep function, and several customization options. These options allow users to tailor the computation process, such as max solutions for the maximum number of series solutions, master series for computing the master series, and print solutions for output format. The package's efficiency is demonstrated through solving the twofold MB representation of the Appel F1 function, showcasing simplicity and efficiency in handling complex mathematical computations. The computational framework is applied to analyze a specific multiloop Feynman integral by utilizing the MB rep and triangulate MB functions. The input for MB rep includes the numerator and denominator gamma functions, along with the indices and exponents of the propagators, which are essential for defining the multiloop integral. This function outputs non-straight contours, indicating that the MB representation has non-straight contours separating the sets of poles of each gamma function in the numerator of the integrand. This result is obtained without specifying explicit values for the parameters a, b1, b2, and c, as they are assumed to be part of the input representation. Subsequently, the triangulate MB function is used to find all possible regular triangulations and the list of series solutions. The matrix associated with this MB integral is provided, which is a key component in the triangulation process. The function identifies a degenerate case with 8 conic hulls and finds 3 regular triangulations. Among these, the shortest series solution has a cardinality of 1, indicating the simplest form of the solution. The paper then details the 3 series solutions found, each with its own set of poles, master series characteristic list, and variables. These solutions are crucial for evaluating the multiloop integral using the MB representation and triangulation method. The computational time taken for these operations is also recorded, demonstrating the efficiency of the proposed framework. In conclusion, this section showcases the practical application of the computational framework in analyzing complex multiloop Feynman integrals. By utilizing the MB rep and triangulate MB functions, researchers can efficiently obtain the MB representation and identify regular triangulations, ultimately leading to the evaluation of the integral. The paper explores the duality between triangulation and conic hull approaches within a degenerate MB representation featuring 8 conic hulls. It showcases the use of evaluate series to derive an analytic expression for a series solution, valid for non-resonant parameter values. This is further validated through sum-all series for numerical evaluation. The accuracy is cross-checked with the Mathematica function Appel F1, ensuring precision. This methodology is particularly significant in solving Feynman integrals, a crucial aspect of quantum field theory. The authors present a comprehensive list of key methodologies and findings in their research paper, focusing on the intersection of advanced technologies and societal implications. They delve into the complexities of integrating these technologies into existing systems, highlighting both potential benefits and challenges. One significant aspect of the paper is its exploration of ethical considerations that arise from the implementation of such technologies. The authors emphasize the need for careful planning and regulation to ensure these advancements serve the greater good rather than exacerbating existing social disparities. In terms of technical details, the paper discusses various algorithms and mathematical models used to predict outcomes and optimize performance. These models are designed to account for numerous variables, including user behavior, system capacity, and external factors that could influence the efficacy of the technologies. The authors also touch upon the limitations of their study, acknowledging the need for further research in certain areas. They suggest that future studies should focus on addressing these gaps and refining the methodologies presented in this paper. Overall, the paper provides a detailed analysis of the complex interplay between technology and society, emphasizing the importance of responsible innovation and careful consideration of potential consequences. The following section presents a detailed overview of the mathematical framework underlying the proposed methodology. Specifically, it outlines the fundamental equations governing the dynamics of the system, including the Navier-Stokes equations, the continuity equation, and the energy equation. These equations are discretized using the finite element method, which is employed to approximate the solution of the nonlinear partial differential equations. The authors also introduce a novel stabilization technique, termed the streamline upwind Petrov-Galerkin (SUPG) method, to mitigate the effects of numerical oscillations and ensure stability of the numerical solution. This technique is shown to be particularly effective in capturing the complex flow features and accurately resolving the velocity and pressure fields. Furthermore, the paper presents a detailed analysis of the boundary conditions and their implementation, highlighting the importance of accurately modeling the inlet and outlet flows, as well as the wall boundary conditions. The authors also discuss the role of turbulence modeling and its impact on the overall accuracy of the simulation. The numerical solution is validated through a series of benchmark tests, including the simulation of a turbulent channel flow and a turbulent flow over a backward-facing step. The results demonstrate excellent agreement with experimental data and established numerical solutions, thereby verifying the accuracy and robustness of the proposed methodology. The page concludes by highlighting the significance of the proposed framework in enabling the simulation of complex fluid flow problems, and its potential applications in various fields, including aerospace engineering, chemical engineering, and biomedical engineering.